Hey everyone, so in this video we're going to be talking about confidence intervals, and it's going to be the second video in a series of videos about confidence intervals. So just a review of what confidence intervals are, remember we talked about point estimates such as x bar, and we talked about how we don't like to use them usually because they don't quantify any of the uncertainty that comes along with the estimate. And we use confidence intervals to provide both an interval and a confidence level in an attempt to provide an estimate for the true population mean mu. So when we're calculating a confidence interval for a mean with a known standard deviation, we use this formula right here. And we went over a couple examples of that in the previous video. So now we can extend this same idea to proportions. So we built a confidence interval around x bar to provide an estimate for mu, and we could do the same thing with p hat to provide an estimate for p, the population proportion. The concept is the exact same as before, except now we're just going to have a different formula. So the formula here is going to be p hat plus or minus z alpha half times the square root of p hat times 1 minus p hat over n. So just like before, z alpha half, which is this piece right here, that's going to be our critical value. The square root of p hat times 1 minus p hat over n is going to be our standard error, which is this piece right here. And then this whole thing right here, which is this piece right here, that's going to be our margin of error, just like before when we were doing this with the sample mean. So let's look at an example. So let's suppose a large company wants to test the interest of a proposed product. And they survey some people, and 220 out of 400 people said they'd be interested in purchasing the product. And then we're asked to construct a 95% confidence interval for the true proportion of people who are interested in purchasing the product. So, as always, I always recommend listing out all the information you have available. So n in this case is going to be 400 because 400 people were polled. And then p hat is going to be x over n. So this was the number of people who said they were interested over the total number of people polled. So 220 over 400 is 0.55. And then we're using z to construct a 95% confidence interval here. And remember from the last video, anytime we're using z to construct a 95% confidence interval, we're going to be using 1.96 as our critical value. So now we have all of the inputs to the formula, and we could just put them right in. So the formula is going to be p hat plus or minus z alpha half times the standard error. So that's going to be 0.55 plus or minus 1.96 times the square root of 0.55 times 1 minus 0.55 over 400. And that gives us 0.55 plus or minus 0.0488. And it gives us this interval right here. So just like before, we're going to interpret this in a similar way. We're 95% confident that the true proportion of people willing to purchase the product is between 0.5012 and 0.5988. So just like with means, we can calculate a sample size needed for proportions as well. And sometimes we're interested in keeping the margin of error lower than a certain number while maintaining a certain level of confidence. And again, the only way to increase confidence and make the confidence interval smaller at the same time is to increase the sample size. And this should make some sense because as the sample size increases, that means we're getting more and more evidence. And when we're getting more and more evidence, we could increase our confidence level or we could make the interval narrower at the same level of confidence, or we could do both. We can increase our confidence level and make the interval smaller at the same time. So that gives us a better estimate for our population parameter. But the only problem is that increasing the sample size means gathering more data, which, as we talked about before, that can be costly in the real world sometimes. So we'd like to avoid doing that as much as possible if we don't need to. So the sample size needed calculation is very similar to before, like when we were dealing with sample means. So the minimum sample size required for a 100 times 1 minus alpha percent confidence interval for the population proportion p is equal to p hat times 1 minus p hat times z alpha half over b squared. And just like before, b is going to be our margin of error. Now, one thing to note here is that if p hat is not given in the problem, then we have to use p hat equal to 0.5 because that's what provides the most conservative estimate for the sample size needed. Because using other values of p hat may underestimate the sample size needed. And why do we know this? Well, it all comes down to this part of the formula right here. We actually want to maximize this whole formula as much as possible because the last thing we want to do is make this quantity too small and then tell ourselves that we have a sufficient sample size when we really don't. So we want the value of p hat that maximizes this whole thing. And it really comes down to maximizing this right here. And the value of p hat that maximizes that quantity right there is 0.5. And by maximizing this whole quantity here, that guarantees that we will not underestimate the sample size that we need. So that's why we use p hat equals 0.5 if we do not have a value of p hat available. So a couple other things to note here. Just like when we were dealing with means, we always round up when we're doing our sample size needed calculations. And remember, we're assuming that the distribution is approximately normal, or exactly normal, but at least approximately normal. So we do have to still check our conditions to make sure it's appropriate to do this calculation in the first place. And remember, our conditions for normality with proportions was that n times p hat needed to be greater than or equal to 5, and n times 1 minus p hat also needed to be greater than or equal to 5. So looking back to the example from earlier, we had p hat equal to 0.55, and we were working with 95% confidence, so that gave us a critical value of 1.96. So now, how big of a sample size would we need if we want to be 95% confident that p hat is within 0.04 of p? And this verbiage right here, the within 0.04 of p, tells us that the margin of error is going to be 0.04 here. So our sample size needed is going to be 0.55 times 1 minus 0.55 times 1.96, which was our critical value, divided by 0.04, which was our margin of error, all of that squared, which gives us 594.25. And again, we're going to round up here. So that gives us a sample size needed of 595. So we'd need a sample size of 595 to be 95% confident that p hat is within 0.04 of p. So anyway, that's all for this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.